Okay, so we start. Good morning, everybody. How was yesterday's contest? A little bit hard. Do you like it? Okay, so I think the next ones will be also a little bit hard. So, okay, so today we will talk about the problems from yesterday's contest. We try to do it in the order of difficulty. So we will start with the problem important meeting. Okay, so in this problem we had up to 1 million segments, and each segment has its start and its end, and we are asked to find a part of the line. So, for instance, it could be, well, in this case it will be trivial. A part of the line in which the intersection, when we take an intersection of the segments, at least 4 segments are fully enclosed in this part. So we would like to find the intersection of at least k segments, and we would like to find the longest possible intersection. Okay, so for instance, in this case we have n equal to 4 segments, and if we want to find an intersection of at least at least 4 segments, so if k is equal to 4, then the answer is this range. But if k is equal to 3, we can find a longer intersection, because we can move this boundary here, and then we have such a range. We just take the first segment, the third segment, and the fourth segment, and this is the intersection. Probably the intersection when we take first one, the second one, and fourth one is also looks long. I'm not sure how they compare on this image, but you get the idea. Okay. So we'll start with some maybe naive algorithms, and then we'll try to gradually improve them to get a good time complexity. So. So what would be like the most naive way to do this? Of course, we can take like every possible tuplet of k segments and calculate their intersection, and among all this intersection we would take the longest one. Of course, this is not a very good idea, because we would get an exponential algorithm. So it's good to make one observation here, namely that it's not it's not a coincidence that there's the range, the best range we have here. It starts and ends in some. It starts in some point in which one of the segments starts, and it ends in some point in which one of the segments ends. So basically, every intersection of the segments must have a start in a point which is a starting point of a segment, and it will have an end in an ending point. So basically, that gives us n to the power of 2 candidates for intersections. Okay, so we are taking every, we are just looping over every possible starting point of the segment, every possible ending point of the segment, and we have a candidate for an intersection. So, for instance, if we have we could just try to like take this beginning and maybe this end. Okay, so this is our candidate for the range, which is an intersection. And now we need to calculate how many of the segments are really enclosed in this intersections. So we can make another loop over all possible segments, and we'll just count how many of them are fully enclosed in this. So if we have if our range starts in A, so let's say this will be a segment I, this will be segment J. So if our range starts in AI and ends in BJ, so we need to loop over all segments K, and we just need to check whether AK is no larger than AI and BK is no less than BJ. So maybe K is not a good letter because this is the parameter of the tasks, so maybe letter L. And we just calculate the number of these segments, which satisfies this property. And if this number is at least K, then we know that this intersection is okay. And we can update the maximal length of the intersection. Okay, so what is the time complexity of this algorithm? It's n cubed, right? Because we have n squared candidates for intersections, and for every intersection we are looping over all segments, so it is n to the power of 3. So it's not very good if we look at the constraints that n can be up to 1 million, but we are just starting. Okay, so usually when you try to improve the time complexity of some naive algorithm, we can look at the do we make some work more than necessary? So do we have some work which we do constantly? And actually yes, because here for every possible range, we once again traverse all the segments to check whether they are in this range or not. So we can try to make it more efficient. And one way to do this is actually we don't want we won't like fix the whole range of the intersection. We will only fix one end of this intersection, end of the candidate. So we will say, okay, so now our intersection starts in AI and it ends somewhere. So instead of fixing 2 values, we are fixing only 1 value. Okay, and now we are asking ourselves, where can this range end? Okay, so basically, if we look at our in our segments, if the segment is in the intersection, it has to start before AI, and it has to end after AI. So, for instance, these guys won't be in this intersection, but these guys will be. So maybe let's draw some more segments here. Okay, and now we would like to see where we can have the end of this intersection. So we need to have at least k segments. So we can go with this bi until we have the last kth segment by the end. So we just okay. So maybe from the other end, we need to have at least k segments in this intersection. So we can look at the endings of this of the segments which are in the intersection, and if we sort these endings from the end to the beginning, we just need to take as kth segment. Okay, so for instance, if k is equal to 2, then this will be the first segment. This will be the second, the third, and the fourth, starting from the end to the beginning. So from right to left. So if you want to have two segments in the intersection, the last segment we can take the longest ones. So we will take 1 and we will take 2, and this will be an intersection which has at least 2 segments. If we want to have 3 segments in the intersection, then we would have to take also this segment. So basically, we need to sort segments which intersects AI. So we take only segments which intersects this point AI, and we sort them. We sort segments by their ends. So by bi, and we just take kth largest. And we just take kth largest segment from the end, and this will be the ending point of the longest candidate for the intersection, which starts in point AI. Okay, so now what is the time complexity? Okay, n log n, we get n log n just by sorting segments for the fixed point AI. So if we want to try every possible point AI, we need to test n times of this. We need to make n times the sorting. So this algorithm will run in time n squared log n. Yes. So essentially, what you are saying is you are proposing how to speed up this this algorithm, and this is a good idea. So basically, once again, we are doing a lot of unnecessary work because, like, we are sorting the segments and like taking the kth largest for every for every possible starting point. We are starting the work from scratch, and actually we can do better. We can try to like to have some data structures which we in which we will store all the segments which are intersecting our current starting position. So when we will be changing our starting position, we will be adding some more segments or removing some more segments. So this structure we will need a structure which allows us to add and remove elements, and we will need the structure to tell us the kth largest element in the structure. So the idea is as follows: we will go with AI from left to the right, and for every possible AI, we do three things. First, we need to introduce new points. So the next candidate for AI will be this point. So we need to put into our structure this segment, because this segment will start intersecting the new point AI. We also need to remove some segments because, for instance, such a segment, it was intersecting AI, but now it is not intersecting. So we need to remove this from the structure. And every time we need to take kth largest segment from the structure. So actually we don't need to like put the segments. We can put like the ending positions. So we just need some kind of set which allows us to put numbers and take the kth largest number. Okay, so how to make such a structure? So the structure needs operations at, or maybe at. It's not. Let's say insert. So insert number in the structure, remove some number, and get kth largest number in the structure. So we would like to have these operations. If we have a structure with these operations in time log n, where n is the number of elements in the structure, then the whole algorithm will run in time n log n, as you said. So then the algorithm runs in n log n. Okay, so unfortunately, like the standard set from C++ library doesn't have this last operation, getting the kth largest element, but it's actually quite easy to implement this kind of structure by hand using two heaps. So basically, you have.
Was the search and eliminate element after the situation to KLM.
Yes, we will get to this. Okay. So basically, for this structure, you could use two heaps. Basically, in one heap, you would have k. In one heap, we would have k largest elements, and in the other heap, you would have other elements. And this would be a min heap. So basically, in the root of the heap, you have the minimal element, and this one will be a max heap. Okay, so if you have this kind of structure, then getting the kth largest element is easy, because this is the root of the second heap. And every time you want to insert some element, so if you want to insert element, you first of all you must see whether it goes into the larger heap or into the smaller one. So if it's let's say this element is S, and if you want to insert an element which is smaller than S, then we'll just insert it into the in this first heap. And if this element is greater than S, then we will insert it into this larger heap, but then this heap will consist of k plus 1 elements. So we will remove the maximal element from the second heap and move it to the first heap. So like we constantly having an invariant that the second heap has exactly k elements. Well, actually in practice it could have a smaller number of elements if we don't have enough segments, but it's still okay. Then this function get kth largest would need to like signal some this condition. But essentially, invariant says that this heap cannot have more than k elements. Okay, for remove, we do essentially the same. If we are doing this by real heaps, we need to have some pointers inside of heaps to get the correct elements to remove. But still, it can be done. Well, actually, we don't need to store it by heaps. We can use normal sets, and then in normal set we can insert element, remove elements, and take the minimal and maximal element all of in log n. So these two structures can be also C++ sets. Okay, and this structure allows us to do all of these operations in logarithmic time. But actually, in this task, we don't need this structure, because we can make one more observation. We would need this structure if we the problem is with removing. Because if we want to insert and remove arbitrary elements, then we would need this. But actually, in our task, we are removing. When we are removing elements, we know that these elements are essentially the smallest elements in the structure. Yes, because we are like moving this candidate II from left to right, So essentially, if you want to remove some segments from the structure, we know that this is the smallest segment in the structure. So actually, we don't need like general remove. We need a remove minimal element. And thanks to that, we know that actually we do not need to store these other elements at all. We only need to store k largest elements in the structure. The other elements we are not interested in. So basically what we are doing here, we just have a set which allows us to insert element, and when the number of elements in the set is greater than k, we just erase the smallest element. They are not. They will never be a good candidate for the get kth largest value. So essentially, we can just have this one structure in the set. And basically that's it. That will also give us n log n complexity. Thank you. Oh, thank you. Okay, any questions? Okay. The second task was banknotes. So I think we don't need to spend like much time on this problem, because it was related directly to what we talked about on yesterday's lecture. So basically, the task was asking for implementing a knapsack problem with bounded version and with costs. So actually, this was the you can make this in time n times m using the min q with minimum, and we talked about it in detail yesterday. Yeah, one thing which was also required in this problem was that we not only need to calculate the best, the optimal cost, we also need to calculate the actual items we were putting into the knapsack. So basically, we need to have this quadratic memory in order to retrieve the result. But other than this, the algorithm is pretty much, we covered it yesterday. Okay. Okay, so now we will go to the task with the hard title. So the task about holes in the ground. Okay. Okay, so the task statement was as follows. We have a long row of holes in the ground, and each hole has its depth, and we have at most, I don't know, 2 million, something like this. 2 million holes in the ground. Okay, and we would like to level some continuous part of these holes, and we have two ways to do this. We have some bags of sand, which allows us to put sand in some holes. So, for instance, we could put sand here, and we could put some sand here, and we have a limit of the amounts of sand we have. And the second thing we have is a long plank, which allows us to cover the continuous segment of D holes. So this has length D. So in this image we have D equals to 3, and if we have enough sand to fill this hole and this hole, we have our answer here is 5. So we can cover up to 5 continuous spaces. Okay. So the question was, what is the longest possible segment we can achieve using the plank and the bags of sand? So once again, we can start with the, I would say, most naive idea, because we can try to test every possible segment which could be a candidate for an answer. So we can try every possible beginning. So let's say here, every possible ending. So let's here, and this would give us n squared possible candidates. And for each candidate, we also need to see where the plank should go. So once again, we have n possible placement of the plank. So the question is, if we know that we would like to be so this segment, if you want this segment to be an answer, we know that we covered these guys with these holes with the plank. So now we know that these and these holes must be filled with sand. So basically, we need to calculate what is the sum of depths of these holes and these holes. Once again, we can do it in naive way, but of course we know that we can do better by using prefix sums. So we calculate prefix sums for this sequence of heights, and it will allow us to calculate in constant time what is the sum of heights here and what is the sum of heights here. So for every such candidate, we get the answer in constant time, and if sum of heights is smaller than equal of the number of bags of sand we have, I think it's denoted by P, then we know that this is the good candidate for the answer. So basically, this algorithm is n to the power of 3. Okay, how to speed it up? Well, we can use binary search over the answer. So basically, we are doing the observation that if we have some candidate and if it turns up that this candidate is a valid one, so the sum of heights of this in this range when we put a Planck here is smaller or equal than P, then we know that every smaller candidate, so every candidate which is like which is contained, every range which is smaller and which is contained here, is also a good range. So actually, in the other way, if we have the range which is not good, then every larger range which will be also not good. So actually, we can, if we this will be the answer, we can make a binary search over the answer, of the length of the answer. So then we know if we fix the length of the segment, so then we basically know that that we need to put these segments of this length in every position. So then we have only n positions, not n squared. And then again, if we put a Planck in every position inside, we got another n, and we have log n. Well, yeah, we have log n from the binary search. So this will give us n squared log n. So basically, we are improving the naive solution by introducing binary search over the answer. Okay. So one thing which we are doing quite naive still is finding the best possible placement of the Planck inside of this range which like to fill. So we have this range, and basically what we are doing here, we test every possible position of the Planck, such that and we want to have that the sum of heights here and the sum of heights here is smaller or equal to P. Okay, so if we would like to find such a position that these sums are smaller or equal to P, so what will be the best position? Like what should we optimize in finding this position? So basically, if some of these guys here and here, we would like them to be smaller or equal to P, then we would like to actually minimize the sum of these guys. But this is the same as actually maximizing the sum of elements which will be covered by Planck. Okay, so we would like to find a position for this Planck which will maximize this sum. And we are doing this in such a way that if we test every position of this Planck, it's of course not very efficient. So what can we do to improve the complexity? We can first of all. So let's say that in this first range we do it naively. So basically, for every position of plank, we will calculate the sum of heights. So let's say this is sum of heights for every position of this plank in this segment, and then from this we will just take a maximum. Okay, so this will be a linear time for one range, but observe that we are calculating more ranges, and actually all the ranges we are calculating have the length equal to uns, and we are calculating them one by one. So actually what we are doing in the next step, we would like to calculate the value for the range which is shifted by one position to the right. So essentially, most of these guys will stay the same. So we are just removing this placement of the plank, because now it is outside of this new range, and we are introducing a new placement of the plank, and this is like the sum of elements which are each were in this plank. And we need to get the maximum from these guys. Okay, so what can we use here? Yes, we can use the technique of the sliding window we used yesterday. So essentially, we can use a min q here. Actually, this q will need to calculate the maximum, but this is really doesn't matter. Either you can like implement this q to get you a maximum, or you can use the min q and put just every time you want to insert an element x, you just insert minus x, and then the minimum q will return you the maximum. So we can use here min q, and you will get we will get every answer to every range in amortized constant time. So what is the time complexity now? So we still have a binary search over the answer. So we have log n, and we need to calculate every range of this length. So we need to like slide this window over the whole segment. So this is n. So overall, we get the time complexity of n log n. Okay, can we do better? Yes? Okay. So that is correct. We can remove binary search and introduce the caterpillar method, or the method of two pointers, because we can do another observation. So if we have a range which is okay, so if we have some range which in which we can find a position of the plank that we can fill the rest of the positions with sand, then we know that the smallest ranges are also okay. So we can try to increase this range to the right. And if we find the first position in which this range will not be able to fill the rest of the position with sand, we know, so this range will be bad. We know that all the ranges which are further are also bad because they're just longer. So they will need more. They will just have more holes to fill with sand. So actually, we can do. We don't do binary search, but we start with the range, and we try to get as long range which starts at position 0 as possible. And when we find the longest range, then we will just take the left pointer into the next position, and then we try to find the longest range again. So basically, we are starting in position 1. We are trying to find the longest possible range which starts here. So we are advancing the right pointer. And when this is like the last range which is okay, we'll just advance the left pointer here. So we know that this whole range from 0 to the right pointer was the last which was okay. So we know that if we advanced this guy here, so we know that this shorter range is also okay. So we don't have to calculate every possible range starting from 1. We know that we can start from the actual position of the right pointer, and then we just update it. So that's like you said. This is this idea of having 2 pointers which goes into over our range. So it is something like the sliding window, but this window can have different dimensions. But we know that we can use our min q here, because as you remember, in our min q we don't have assumption that the sliding window must have the same size every time. We can just adding and removing elements separately, as long as we add in on the one end of the segment, and we are removing on the other end of the segment. So basically, we are just doing this min q here, and this algorithm we will have a linear solution. Okay, so that's it. Any questions?
When you write on the board, try to write
Bigger letters. Okay, I will try. Okay, so maybe here. So the next task, which will be difference. So in this task we have a word of n letters, n is up to 1 million. Okay, and once again, we would like to find some kind of the best fragment of the here we will have a word, And we would like to find the best fragment in which the difference between the letter which occurs most frequently in this fragment and the letter which occurs least frequently in this fragment is as big as possible. So, for instance, if we take this fragment here, we have number of letters A is 3, number of letters B is 2, and number of letters C is 1, and number of letters E is 0, and every other letter is 0. So we take the letter which occurs most frequently, this is A, and least frequently, but it must be at least one letter in the range, so this will be C. So for this range, the answer is 3 minus 1, and it equals to 2. It's easy to see that we can improve this. For instance, if we take this range, the number of letters C is still 1, but the number of C's is 1, and number of letters A is 1, 2, 3, 4, 5, 6, 7 letters A. So for this range, the answer is 6. And we would like to get the range with the best answer. So once again, if we try to take every possible range, it will give us at least n squared times the number of operations we need to calculate the most frequent letter and the least frequent letter. So actually, if we do a prefix sums over every possible letter, so then we can calculate in constant time for every letter and for every range what is the number of this occurrences of this letter in the range. So we can have basically prefix sums for every possible letter, and the number of letters, the size of alphabet was limited by 26, the standard English alphabet. So we can afford to calculate these prefix sums. So prefix sums, we can calculate them in time n times the size of the alphabet. So if we have these prefix sums, we can, for every range, we can in constant time calculate the amount of letters. So we can, for every possible range, we can go through every possible letter and then pick the maximal one and minimal one. And this will result in algorithm n squared times the size of the alphabet. Okay, but this is not very efficient because the length of the word is big and the size of the alphabet is small. So we would like to have it reversed. So the better would be a squared times n. So instead of taking every possible range and then seeing what kind of letters there are in this range, we can take every possible pair of letters and try to find out the range in which the first letter from the pair appears most frequently, the second letter from the range appears least frequently, and this range is as long as possible. So what we can do here, so we take every pair of letters take every pair of letters, let's call it AB, and assume that A is most frequent and B is least frequent. And with this assumption, we would like to find a range which is the longest possible range which satisfies this assumption that A is most frequent and B is least frequent. Okay, so how can we do this here? So let's maybe do this on this example, and I will change the names of the letters. So let's say that A is most frequent and C is least frequent, and we try to do this for this example. Okay. So basically, this boils down to if you want to find the the number of letters A which is most frequent minus the number of letters which is least frequent, then for every letter A we would add 1 to the answer, and for every letter B, for every letter C, we would put -1 to the answer. So basically, for every letter A, we have 1, and for every letter C, we have -1. And for every other letter, we are not interested in them, so we can put 0 here. So for every letter B and for letter E, we have 0. So in this terminology, we would like to find a range which has the greatest sum. So for instance, this range here, it has the sum of 7 plus -1 equals to 6, and this is like this best range we have. So basically, it boils down to the standard algorithm of finding the continuous fragment in the array, which has the maximal sum. But here we have, so find a fragment of maximum sum. So we know that there's a standard linear algorithm for this. So this can be done in linear time. But here we have one additional requirement which we need to take care of, because not every fragment is the best one, because we need to have at least one letter C in this fragment. So the fragment of maximum sum with at least one -1 element. Okay, so this is the distinction from the standard formulation. Okay, so how can we do this? Well, actually, it's quite easy to adapt this standard algorithm, because how the standard algorithm works. Basically, if we want to find some fragment with maximal sum, so let's say that we have some word And we will be adding letters one by one to this word. So actually, this is not. We are not having a word anymore. We have just zeros and ones. So in the standard algorithm, we are adding numbers one by one, and for every position. So actually, for every prefix, we would like to know what is the maximal sum which ends in this position. So we would like to know what is maximal sum which ends here at this position. So basically, it's the same as finding the minimal sum minimal sum of the prefix. So we would like to find the prefix of minimal sum. So basically, we are adding one number at a time, and we are keeping track of the current sum of the whole prefix and the minimal prefix we have found so far. So we are just tracking two pieces of information. So we are tracking the current sum and prefix of minimal sum. And for each pair sum and prefix of minimal sum, we have a candidate for the maximal sum here. Okay, but now we would like to introduce this this requirement that we have at least one -1 element. So basically, not every minimal prefix will be okay, because we need to take care of that at least one -1 is stored in this maximal sum. So basically, we will not calculate the prefix of minimal sum, but prefix of minimal sum without prefix without last -1. So basically, we will need to track of this prefix. So we can have like the prefix of minimal sum without last -1 and real prefix of minimal sum. And when we encounter another -1, we say, okay, so now this maximal prefix of minimal sum here doesn't have the last -1. So this can be a real prefix of minimal sum without last -1. And this is basically it. So it's also done in linear time. So what is the time complexity of whole algorithm? So for every pair of letters, and we have a square such pairs, we need to run this algorithm in linear time. So this is a squared times n. Okay, so how can we speed it up?
We go to perfecto, which only update one fifth letter.
Okay. So one thing to notice here is we have this pair of letters. We have letter A and we have letter C, and these letters are interesting ones. So these are letters for which we put ones and -1 into our in our word, but we have all these other letters. Like we have letter B, letter E, and actually, if our alphabet has like 26 letters, and we have different letters in our word, so possibly most of these letters will be actually 0. They won't be A or C, they will be like E, F, G, H, I, and so on. So at least for some choice of A and C, most of the elements in this sequence will be 0. And actually they don't, because we are not calculating like the longest range, but the range which has the greatest number of A's and smallest number of C's. So if we like remove some kind of zeros from the range, from the word, it doesn't really matter. And actually, it will be nice to remove them because they are introducing unnecessary work for the algorithm, which just adds another zeros, and it doesn't really matter. Okay, so let's say that we removed all the zeros. Can we see that our complexity can improve here? Yes. So basically, the first question is, how can we remove zeros efficiently? Because if we just say, okay, take every pair, and now from this sequence remove all the zeros, and then run this algorithm, then we don't have any improvement here, because to remove all the zeros, we still need to go through the whole sequence in linear time. It would be an improvement, for instance, if this algorithm here would, if it would be quadratic, then perhaps we have an improvement. But it's linear, so we cannot go through the whole sequence in linear time. But what we can do, we can actually construct this sequence of ones and -1s without constructing zeros. So basically, at the beginning of the program, we calculated this prefix sums for every letter, but also we will construct a list of positions for every letter. So prefix sums, and we have lists of positions. And it also can be, well, the list of positions even can be constructed in linear time, because the sum of the lists will be linear. So basically, for every letter, so it will be n plus a. So for every letter we are putting the position of this letter to one of the A lists. And then if we want to take a pair of letters AC, we just take a list of letter A, take the list of letter C, and we make a union of this list. These lists are sorted, so taking a union of two sorted lists will be linear, so it will be okay. So actually, this complexity here, linear, will be not in the size of the whole in the whole world, but only on the numbers of. So this will be linear in the numbers of letter A plus number of letter C. Okay, and we can see that every particular letter from the word. So, for instance, this letter A, it will be used as in this algorithm for every other possible letter. So this particular position here will be used when we are considering pairs A, B, A, C, A, D, and so on. So this letter will be used at least at most 2 times 8 times. So this letter will be in all of A pairs. And we have n letters in total. So this will mean that the improvement of this algorithm is to A times n. And this is the final complexity here. And okay, and okay. So actually, this is the valid question. So as I understand the question, it is something like this. Maybe I can remove here. Okay, so what we are saying that we have we are considering letters A and C, and we have, let's say that we found some okay, so let's say that we have found this range. This is the best range for A and C. We calculate this as a candidate. So let's say that 4, 5, 6, 7, 8, 9, like 10 number of A's, and we have 1, 2, 3, 4 C's. Yes. But actually, for this range, if we see this range doesn't have the answer 10 minus 4, because actually the letter C is not the least frequent. Yes, this is what you are saying. Okay. So basically, for this range, number of letters F is 1. So the answer for this range is actually 10 minus 1. So when we calculate this range as a considering only A and C, we will find that 6 is the candidate for the answer. But we are at the moment we are not saying that this is like the best answer we have. And actually, we will get this answer 10 minus 1, or at least this answer, when we will be considering the pairs A and F. Zach? So, but you're right that this is like, we need to clarify this, that when we are considering A and C, the range which we will find in this algorithm not necessarily will have A and C in this range. Not necessarily A will be the most frequent and C will be the least frequent. Yeah, so that's a good observation. But if it's not the case, then this range will pop out when we are really considering A and F. So for A and C, this is not a valid range, but it doesn't really matter, because when we will consider A and F, this range will also probably pop out, or some even better range with A and F. Okay. Okay, so let's talk about one more problem, and we will have a break. So now a little bit of geometry. So the problem pawn. Okay, so in this problem we have some we have a plane, and on the plane we have in the center of this plane we have a pawn, which have some a set of valid moves, and every move is represented as a two-dimensional vector. So, for instance, these are like possible moves of the pawn, and the number of these moves was like 200,000. Okay, and every move can be used at most once, and we would like to do some moves. And after doing this certain moves, so for instance, if we do this move and then this one, the pawn will be here. And if we do also this move, the position of the pawn will be here. And we would like to calculate such a position which is as far as possible from the initial position of the point. So we would like to find a position which can be achieved, and the length of this dashed segment is as long as possible. Okay. So idea is as follows. So suppose that we found an optimal solution. Somebody tells us, okay, the optimal solution is, for instance, located here. And he's asking us, okay, show me the moves which enables the pawn to go into this position. So we see that some moves are good and some moves are really bad if we want to go to this position. For instance, if this move which goes upwards, it's not very good to use it, because this move will move the pawn further from the desired position. So actually, we don't want to use this move when going here. But on the other hand, this move is quite good because it will it is like the move into good direction. What about this move? Well, this move looks like somehow good because it doesn't really go into precise direction, but at least on one coordinate it goes here. So basically what we are trying to say is we would like to go in this direction. So pretty much if we draw a line which is perpendicular to the to this direction, pretty much every move, so every vector which is on this side of this line is bad because it doesn't incorporate any it doesn't make any progress towards this this goal. And actually we can take every move which is in this plane. So actually how to prove this a little bit more formally, why every such move could be okay. So once again, let's write the center of the so the starting point of the of our pawn, and let's draw every possible move. So every possible place when this pawn can be moved to. So we are considering every possible set of moves. So this will give us some possible places where this pawn can be moved to. And from these possible places, we would like to get the furthest one. Yes. So it's not very hard to see that one of the furthest one must be on the convex hull of all these elements. So if we take the convex hull here, the one of the farthest guy must be on the on this convex hull, because clearly these guys inside are they have some guy on the convex hull which is farther from the center. And as you can see, the guys on the convex hull they have this. If we take the direction to this guy, let's see that like we can take this this plane perpendicular here, and if we take this plane here, then actually every move here will be like every move which is on this side of the plane. It will advance us to this line. So it will be better for us to go, because we would like to go as to this point, but it really doesn't matter if we go exactly to this point or if we go, for instance, to this point, because this point is even further from the center than this one. So as long as we are making progress in this direction, so as long as at least so if we are making some progress in this direction, it doesn't really matter whether we are taking some additional progress here or some additional progress here. Because what is really matters is if we are going closer to this line. Okay, so basically that's it. Because of course we do not know this point. We don't know the position of this point, but we know that for the optimal point there is some plane. So there is some semi-plane of the vectors, and if we take all the vectors from this semi-plane, we will get to the optimal point. So the idea is to okay, we can test every possible semi-plane. So we can take every possible semi-plane, and then for this semi-plane we can take all the vectors which are located in the semi-plane and add these vectors, and this will be a candidate for an answer. So the question now is how to efficiently calculate all the semi-planes. Well, like in theory, the number of possible semi-planes which goes through the point 0, 0 is infinite, but we know that there are finite number of these semi-planes which gives the different sets of vectors. So if we have this point 0, 0, and we have some vectors, so for this set, for instance, we can start with one semi-plane, and for this semi-plane we will take this guy and this guy, and what we can do, we can start rotating this semi-plane. And when we rotate this semi-plane, some vectors will enter the semi-plane. So for instance, if this is a new position of the semi-plane here, this vector will enter the semi-plane, and some vectors will be removed from the semi-plane. So basically, this is this idea is the same as this idea with this task when we have left and right pointer. So basically, what we have here, we also have left pointer and right pointer. So the pointers to the first vector in the semi-plane and the last vector in the semi-plane, as long as these vectors are sorted in the along the point 0, 0, and we just move the semi-plane. Of course, if we like the valid possible positions in the semi-plane are also finite. Yes, because it doesn't really matter if this semi-plane is here or is a little bit further, as long as the set of the vectors is the same. So we can stop this semi-plane at the positions of the vectors. So actually, for every if the semi-plane is in some position, we need to consider two new positions. One position is the closest new left pointer, and the second position is the actually removing the last right pointer, and we'll taking the position which will change the semi-plane as little as possible. And as we revolve this semi-plane, if we do a full circle, then we considered every position, every possible semi-planes. So first of all, we need to sort all of the vectors along along the point 0, 0, and this can be done in n log n. And then we need to do this algorithm of revolving semiplanes, and this can be done just in linear time. Of course, we need to not only store which segments are, which vectors are in the semiplane, we also need to store the current sum of all these vectors. But this can be updated in constant time when, like when we adding new vector, we just add it to the sum. When we removing the vector, we just subtract this vector from the sum. And at the end, we are just returning the, and we are keeping the current maximum, and we are returning this maximum at the end. So in total, this algorithm works in time and log n. But of course, as with geometry problems, you have to be quite careful in considering every corner case doing this this revolving. So this can, so like the idea is this, and in terms of programming, this can be a little bit tricky to get it right. Okay, questions? Okay, so what you are saying is you want to calculate this convex hull and then consider all the points. And how do you, what is the time complexity of calculating this convex hull? I mean, do you calculate all the points inside? Because like, yeah, because this would be too much, because like all these points are from the different sets of moves. Oh, so you want to use divide and conquer. Okay, so I'm not aware of this approach for this task. Okay, but we can talk during the break. You can talk. Okay. Some question here was. Okay, so if there are no more questions, we will take a 10-minute break. Okay. Okay, so I think we'll be starting the second half of the lecture. Okay, so the question from for this pawn problem was, do the algorithm with Minkowski sum works. So basically, the idea was to calculate the Minkowski sum of all the vectors, and it should be this convex whole of these possible points, and then we can and it should have linear number of points, and then we can just take the point which is farther away. I'm not sure if this idea will work. You can test this, but yeah, but this is another idea for the problem. Yes.
What is
I will not go into details here. So if you're, I just write it. If you're interested about this, you can read it. But I think that this is not needed for this problem, and this is a little bit advanced geometry. So I won't be going into details here. Okay, so that will be all for this problem, and we will now go to the problem about cloakroom, and I think I will start here. Okay, so in the task description was as follows. We have some n items, and every item was characterized by 3 values. Essentially, with values ai and bi, where the starting point in time, ai was the starting point in time in which this item was become available, and the bi was the last point in time in which this item was available. So the item is available during this segment, and we have different items which can start and end in different points of time. And also each item has a value ci, which was the cost of this item. Okay, and we have additional queries, and each query would have the following. Was also described by 3 values, and we also can write these values as a, b, and c. So basically, the query asked for something like this. We would like to know whether there exists some subset of items which has the total cost ci, and by total cost we mean the exact cost. So a subset with exactly the sum of the cost is ci, and this subset must be available during the whole range. So from ai to bi, the items from this subset must be available. So for instance, we see that we cannot take these two items. So for this range, these two items are not good because this one is becoming available after AI, and this one is not available through the whole. His BI is less than this BI, but we can consider this, and this element. So we can consider the first, the third, and the fifth item. And among these items, we'd like to take some subset which has the total cost equal to CI, and also the total cost is not greater than CI is less than 10 to 5. Okay, so what does it look like? It looks like some kind of knapsack problem, because we are taking the items which has a certain cost. So basically, it looks like some kind of algorithms we talked yesterday. But the problem with this, we have a little more variation here, because we have this additional requirements or constraints that these items are not available through whole time. They are appearing, and they are disappearing. And the second thing is, here in the task we talked about the costs of these items. So actually, this is not the cost we were talking about yesterday, because when we are here in the task, we would like to take the items which has precisely some cost. So actually, this cost here corresponds to the weight or to the size which we are talking about yesterday. So one important thing in this, when you see a task which looks like it could be related to a knapsack problem, is to identify which is actually a weight or the size of the element, and which is real cost or some additional information, because they can be in the task, they can be named in our direction. So actually, if we want to be, if we would like to have the terminology from the previous lecture, we would say that these elements have weights or size, and we'll name it by WI, and this total cost is just a value J from the yesterday's lecture. So this will be a total cost. So actually, the knapsack algorithms from yesterday, they provide us with the structure which allows us to query any possible total cost up to M. So we can say that. So actually, we will be using some of the methods from yesterday. So we'll actually calculating the knapsack structure, which allows us to answering the queries up to M. Okay, so this is the terminology. So basically, if all the AIs were like 0, and all the BIs were like infinity, so with these assumptions, we know how to solve this problem. Yes, because that means that every item is We can take every item, and that means that we need to solve a normal version of the knapsack problem. So we need to solve 0, 1 knapsack without cost. So actually, this is like the basic version of the problem, and we know that the time complexity of this is n times m, and it produces us with the array which allows us to answer any query. So that would be it. If we don't have any time restrictions, we can solve this problem. Okay, so let's try to introduce this new constraints. Okay, and we will introduce them one by one. So let's say that the elements can have different AI, but they will have bi equal to infinity. So that means that the items can appear in some moment in time, but when they appear, they will be available like forever. So basically, what we are having in our picture is, so let's say that AI is is anything, and bi is equal to infinity. So in the picture we will have every item will have some starting point, and each query will also have some starting point. So actually for each query so for each query we are only interested in AI. So we know that if we have some subset which is available here in point and AI, this subset will be like the same subset will be available through infinity. So actually, this really, it doesn't matter what bi is. Bi also can be like anything. Yeah, because if you have smaller bi, it's even better. So it doesn't really matter how big bi is. It all only matters that our items are available forever. Okay, so this is a little bit simpler problem, and can we do it? So actually, when we if we recall this knapsack algorithms from the yesterday's talk, most of these algorithms were done in the same manner. So we added elements one by one. Apart from the more clever algorithms in which we like bundled elements in some groups, the most basic algorithms for knapsack, we were just adding element one by one. So we had this loop. So we initialized the array D, and then we have a loop for every possible item. And then we have a loop for j, and in this part was just updating we'll just update knapsack with element or with item number I. So before this loop, we have a knapsack in which we have elements from 1 to I minus 1. So here we have an array D, which is a knapsack for elements or items I 1 to I minus 1. And after the loop, we have array D, which has items from 1 to I. And this pen is not working anymore. Okay. So basically what we are having here, we have a procedure which adds one element to the knapsack. And what is the time complexity of this procedure? This is M. So we get this time complexity n times m because we have n items, and adding one item to the knapsack costs us O of m. Okay. And what is really important here is that the order in which we are adding the elements to the knapsack, it doesn't really matter. So we can change this order if we like. So this is one observation. The second observation is that if after we update some knapsack with some elements, we can already answer some queries. So for instance, if we put first 3 elements to the knapsack, then we can answer the queries from the array D about the possible subsets which are considering only elements 1, 2, and 3. And every query we can do in constant time. Okay, so that means that we actually can solve this one. Okay, because we can sort every event on the timeline. So what kind of events we have? One event would be appearance of a new item. So for instance, in this moment of time, this item appears. And that means that we can that here we can put this item to the knapsack. In this moment in time, so as we are progressing, another element appears, and in this moment of time, another element appears. So now we have 3 elements in our knapsack. So let's say that we have more elements here. Okay. So what is the next? What is the next event? The next event would be a query. This query. So here we are querying about elements which were inserting into the knapsack before this time. So we are querying about these elements, and we are querying about certain total cost for these elements. Okay. So, but all of these elements which appeared before AI are already in the knapsack, so we can make a query, and then we can add another element to the knapsack, and then we can add another. If we have another query AI here, we can answer it after we add to the knapsack all of the preceding elements. So basically, the algorithm is as follows. So sort all events by AI and AI. So actually we have 2 kinds of events. The new item enters, and we have a query, and we make a vector of all these events, and we sort them by the starting time. And then for every event So for event AI, update Knapsack, and for event AI, answer query. Okay, so one more thing is the number of queries was at most 10 to the 6th. So the sorting is just n plus p, and for every updating of Knapsack we have n updates, and every update costs us m, and for every query we have p queries, and every query is done in constant time. We have n times n plus p. Okay, so from this this constraints will look like this. This algorithm will be accepted. Okay, any questions? Okay, of course we are not done yet, because we still have this simplification that elements do not disappear, and now we try to get rid of these simplifications. Okay, so what we shown here is we can update our knapsack by adding another elements one by one, and after each addition we can do some queries. So actually our knapsack structure allows us to do two operations. We can have an operation insert an element, so insert an element with some weight or some size, and do a query. Does exist any subset with total weight equal to j. So this is our knapsack structure. Unfortunately, we do not have here the remove operation, because if we have a remove operation for the knapsack, then well, at least we need this remove to be able to incorporate the thing that the elements are disappearing. Okay, and unfortunately, it's not very easy to add remove operation to the knapsack. In general, it's there's no easy way to do this, but we can try to figure out how to solve it anyway. Okay, so now we have a more general picture. So we have some elements which has some starting points and ending points. So let's suppose that we have this remove operation from the knapsack. Can we solve this the task in full general? And the problem is, okay, so we can then sort all events, and now we will have different kind of events. We will have events AI. This is like a new item. New item appears. Okay, we will have item events bi, item is removed. And we can sort the events about the items like normal from left to the right. Okay, but the problem is what is happening with the queries? If the queries were just simple points, so we will have if AI is equal to BI, so we are just questioning about is there any subset in this precise moment of time which is of certain total size, then adding items and removing items would be sufficient. But unfortunately, if we have longer periods here, like this one, well, it looks like, okay, so this element is still present here in AI, but it's not present here in BI. So if we have this image, and if you have a second query here, so this item here, the second item, is present for the second query, but it's not fully present for the first query. So it's not very, it doesn't look like we have any sensible way to sort these queries. So let's say that we still need some simplification. So let's say that we have this simplification that AI is equal to BI, so we are like querying only simple points, and this is the query. And let's solve the problem with this simplification. Okay, so how to add operations of removal to the knapsack? So one way to add it would be okay. So first of all, why is it hard? Well, the hard part is this, that if we want to remove an element from the knapsack, we would need to see in what precise total weights this element is necessary. So basically, for the if we have an RID, and this RID just stores ones and zeros depending on whether the element is whether this particular total size is achievable or not. So when we are inserting new element, we basically take all of the ones, and if here we have one, and if this element here has additional weight of 3, then we know that we can put one also here. So we change some zeros to ones. But if we have one here, we also take this one and put one here. So sometimes we do not change 0 to 1, but we are like rewriting this one once again. But it doesn't really matter for us. So, but the problem is, if we want to remove this element 3, then we would like to know what was the, like, do we have to put 0 here in this one, or do we have do this one stays as 1? So we need to know in which subsets this element was necessary, and in which subsets are obtainable using other elements. And unfortunately, the the information in this array is not sufficient for us to calculate this. Okay, but we can try to calculate a little bit more information here. So not only we will calculate whether the certain subset is obtainable or not, but we will calculate how many subsets we have which have the certain weight. So basically, when we are adding a new element here, we are not putting just one here, but we are increasing the number of subsets which can be put here. So basically, when we are making a loop, okay. So normally we made the loop as follows. So here we are adding all elements, and we made a loop from J from okay, we make a loop from M and J was greater than Wi, and we made something like this. D of J is OR with D of J minus Wi. So this was standard approach for the knapsack. We're just putting ones. If this element is 1 equal to 1, we are putting 1 here. Okay, but so dj was just a binary value, and now it will be the number of subsets, number of different subsets of total weight J. Okay, so in this setting, we would need to calculate the number of subsets of size dj, and we know that before adding element I, the number of this value was the correct value for all the subsets. So it was the number of subsets which covers element from 1 to I minus 1. So this was number of subsets for I to from 1 to I minus 1. Okay, and now we need to add the number of subsets which includes element number I. Yes, so how these subsets look like? Every such subset has an element I and has some spare room for some more elements from 1 to I minus 1. And this room is of size j minus the size of the element I. So actually this is number of subsets from so this is number of subsets from 1 to I minus 1 of size j, and this is number of subsets also from these elements of size of this size, but this is also the number of subsets of elements from 1 to I of size j, which includes elements I. So basically, these guys are subsets from elements from 1 to I of size I, which does not include I. Okay? So basically, if you want to take all of the subsets from 1 to I of size j, we need to take a sum of these numbers. Yes, but because this guy already covers all of the subsets which does not include I, and this guy covers all of the subsets of which includes I. So we can just change this to the sum. And of course, this must be properly initialized, but the initialization is the same. So d0. So actually, the number of subsets of size 0 is 1, because this is the empty subset, and for every other subset, if we don't have any elements, is 0. So this is the same as before. Okay, and here we need to also take care of the order of the loop, because like we are changing this array on the fly. But we see again that this new number, after we change this number, no other number will depend on this. It's because we are depending on the smaller numbers, and we are making a loop from the biggest numbers to smaller one. So actually, this loop will correctly calculate the number of different subsets of total weight j. Okay, so this is this loop is inserting element wi. Okay, and why does it help us to make a remove operation? Because if we remember, we are making this to implement a remove operation. So for the remove operation, we now know the exact number of subsets which has a certain total weight j. So now, if we want to remove element I, we can calculate how many of these subsets are actually having element I in them. And how to do this? So if we have some subset, if you have dj subsets of size j, and we have some element of size wi, so how many of these subsets must include this element wi? So this is the number of subsets of size j which must include element wi, because like every subset which which has element wi here is constructed of two parts. This is element wi, and the rest of elements. And the size of the rest of elements is this. So actually, for the removal part, we need to subtract this number from this number. So this is the code for the inserting, and the code for removal is very similar. So where can we put it? Yeah, I would like to use this. All right, this board. Okay, so let's put it here. Okay, so this is inserting, and now we would like to make a remove. Okay, so basically for removal, we'll just have a loop over j, and we will go from, so basically from dj we want to subtract this number. Okay, but now is the crucial part. What is the order of operation? Sorry? Yeah. So this is crucial part here. We need to go from wi to m. Okay, and why is that? The problem is that here we would like to know. How many. Okay, these two numbers tells us how many subsets are of these sizes, which includes also element I. So in order to get a new value here without an element I, we would like to remove all the subsets, all the number of subsets here of this size, but these subsets cannot have this element I, because we want to remove this element I from here. So we would like to partition every subset from here with two parts, element I and everything else of size j minus wi, which does not include element I. So actually, this number must be fixed before we are fixing this number. So now we are making a loop from the smallest element to the largest element, because this number must be updated before we are updating this one. Okay, and this actually will work. So we have an operations for inserting and for the removal in times. Each of the operations works in time O of m. And after each operation, we can do a query which runs in constant time. Okay, so yes. Okay, so this is the good observation here. As I told you before, we cannot. We don't have like the easy way to do the removal of the knapsack, and now we are showing the algorithm which actually does the removal. But the problem is there's quite a serious problem with this algorithm. Namely, we are calculating here the number of different subsets. So what will be the maximal possible number of different subsets of n elements? Yeah. So this number can be as big as 2 to the power of n. So unfortunately, if we have like 1000 elements, we need to store here our big integers. So basically, we need to multiply this time complexity by the logarithm of the size of the number which we are storing inside each cell, if we are using big integers. So actually this must be multiplied by the logarithm of 2 to the power of n. So this is m times n. So actually this is no better than actually calculating the whole knapsack from scratch after removal. Yes, because if we have n elements in the knapsack and adding each element is O times m, so we can like throw away, so to do the removal we can throw away the knapsack and add all the elements which were not removed from scratch, and this will give us the same time complexity. Okay, so it looks like this is not very good, but don't get discouraged. So because like we put a lot of energy to come up with this algorithms, then we need to like let's try to use them anyway. So yeah. So basically this is the idea. We don't want to use big integers because it's an overkill here. Like the time complexity will be bad. So let's say, okay, if we cannot use big integers, we cannot calculate the number of different subsets precisely. So let's say that we calculate them modulo some number. So usually in the task statements, you don't have to calculate the in the combinatorial problems, if the number gets really big, you don't need to calculate the whole answer, because then probably you would need to use big integers. So you're asked to calculate this number modulo some number, usually prime number, as a proof that you can calculate this answer. And usually in this problems, if there's no simpler way to calculate it modulo, so if you are able to calculate it modulo, you are proving that you can calculate the whole answer. Well, sometimes in some problems it's crucial to use this that you are calculating modulo, but usually not. Okay, so we can try to calculate number of different subsets of total width j, number, and this number, okay, can be as big as 2 to the n. So we calculated number modulo, let's say some value p. Okay, since here we have only additions and subtractions, we can easily calculate it modulo p. After each operation, we just take the answer modulo p. Okay, so then if p is fits in one integer, so if p is like smaller than 10 to the 9, once again we can do this in time O of n. Okay, but here we will encounter a problem. Okay, because okay, we are calculating the number of different subsets. So once again, when does the query says yes, there is a certain subset? So for the query, it says yes if dj is greater than 0. Yes? So if we have at least one subset which which has a weight of j, we say true. And if it's 0, then we can say no. Okay, so when we are calculating this number modulo p, we can run into the problem: what if the number of subsets for a certain j was divisible by p? Then in this cell we would have 0 and not a positive integer. And then it's the only case in which we would give a wrong answer. But actually, if p is quite big and it's like a big random number, so actually, what is the probability that the test case will hit this case is quite small. Actually, if you want to construct a test case which will hit this problem, you would need to know this number p to actually construct the precise test which will result in the number of subsets divisible by p. So if, for instance, if p is a big prime number, well, and it's like randomly chosen by you, so there's a really small probability that this will get you into trouble. And even if it gets you into trouble that you got a wrong answer on some tests, yes, you can try different number, yes, and to try to resubmit your solution. So this is also a possibility here. And also the another possibility you mentioned is you can calculate this with a even bigger number, like 64-bit number or something like this. This will give you an even smaller probability. Or you can calculate it several times modulo different prime numbers. So you can have several knapsacks which calculate you modulo different numbers of p, and then if for every prime number you get 0, then you can be pretty much sure that this is really 0. And if for some prime number you get non-zero, then you're answering that the real number is non-zero. So you can increasing your probability by introducing new random prime numbers. Yeah, so probably this would this method would get you accepted problem, but of course it has a small probability of getting error. But unfortunately, this approach does not solve our problem, because once again we have a simplification that the query is only in a single point. So we can make additions and removals of elements. Okay, so we need to do something more clever here. Okay, and I will erase here. Okay, so here we have this simplification that every item has a moment in which it appears, but it will stay forever. Let's make a symmetric case. So let's say that every item, it has some ending point in which it disappears, but every item is like available from the beginning. And we have some queries. Okay, so this looks like this can be done just by reversing the time. It can be done using the exactly same method, but I would like to show you another method which does not reverse time, and it's more more natural if every element has some moment in time in which it disappears. Okay, so one more idea about the knapsack problems is that if we have the very basic knapsack without cost, in RID we are storing just true or false. If we have a knapsack with additional costs, we are using this RID to store some information about the optimal subset. But this RID can be used to store other kind of information, and here we have this the example here. So we are storing additional information, which is the number of different subsets. But we can think about even different information about the subset. And the idea here is, let's take a look at these elements. The items have a moment in time in which they will disappear. So when the item disappear, all of the subsets which are constructed in such a way that they need this item will also disappear. So we can think of it that some subsets will have the subsets will also have a time in which they will disappear. So we are interested, if we are interested in subset of size j, we actually are interested in the last time in which we are interested in the point in time in which the last subset of this size disappears. Okay, and we can store this information in the RIDJ. So now the DJ will be the last moment in time in which we have some subset of size j. Okay, and let's try to add the elements to the knapsack and at the same time calculating these values. So the initialization will be quite easy again. So if we have no elements, then the last moment in time in which we have some subset of size 0, so the empty subset. The empty subset will be available every time. So we can say infinity. And for every other subset, we can say like minus infinity, because we have no such subsets at all. So if the subset is not available at all, we can say that this is minus infinity. Okay. Mm-hmm.
The size of the subset is the number of...
No, it's a subset of size j. It means the subset of total weight J. So J is always total weight of the elements. Okay, so now we can make our standard loop. So we are adding all elements. And we have another loop for J. And as always, we go from M to Wi. Okay, and now we would like to calculate the last moment in time in which we have some subset of total weight J. So first of all, this is the maximal time for the old dj, which includes all the subsets which have elements from 1 to I minus 1. And now we are introducing a new element I. So basically, this new element I will be, if this new element I construct a subset of total weight J, it must take some subset of total weight J minus Wi, and we add just element I to it. Okay, so what will be the last moment in time in which this new subset will be available? Yeah. Okay, so this will be the minimum. So this will be the minimum of the dj minus Wi, because this is the time, the last time in which some subset of this size will be available. Yes, and Bi, because this is the last time in which element I will be available. So this minimum is essentially the last moment in time in which we have some subset which includes element I. And this is the last time for the subsets which does not include element I. So we just take maximum of these two values. Okay? So thanks to this, we calculate in n times m this value last moment in time in which we have some subset. Okay, so now when we have a query, so the query will have some point in time b. Yes, we'll have ai and bi. So we need to see what is the bi, and we need to see whether this bi is not greater than the last moment in time in which have this certain subset. Okay. Okay. So what is the query? So in the query we have like ai, bi, and j, and the query asks us for the subset of total weight j, which is present from ai to bi. So we need to. So we just return whether the last moment in time in which this subset of total weight j appears. This last moment in time must be not smaller than bi. So we can get query in constant time and calculate this in times n times m. Okay, so it looks like we have another another solution for the problem in which we have only in which time is only like limited from the one side. But I deliberately use BI here and AI here, because as you can see, you can merge these two approaches together. Yes, because as you can see here, when considering elements of BI and considering queries, we didn't do any sorting here. So actually here, we can add these elements in any order. So we actually can add this in the order of AIs. So we are inserting so now we are sorting events by AI and II. So we are just doing this sort. We are inserting elements to the knapsack, but when we are inserting elements, we are calculating the minimal time, the last moment in times in which the subsets are available. And thanks to these times, when we encounter a query, we can just use this method to make a query. So once again, the total time complexity of this algorithm is the same, because we are inserting in time of m, and we are making a query in constant time. Yeah, and finally, this is the solution of the problem.
So far, is that approach?
Mm-hmm.
What is
No, we don't. Yeah, we don't have any remove operation here. Yep. Mm-hmm. Okay. Yeah. So the problem is plus minus 1. Yes. Okay. So well, it depends how we treat the endpoints of the segments, but it doesn't really matter. Yeah, this is like the. I think in the task statement, the treating of the endpoints was some kind weird, but the general idea is the same. Okay, so if there are no further questions, that will be all for today. Thank you very much.